Okay, so tungsten analyze the discharge and find out there are two important factors to control the breakdown condition. So once the gas is breakdown, the gas changes from insulating state to conducting state. So from the tungsten analysis, we can find out the number of electrons, number of the newly generated electrons can be represented by the equation of gamma times exponential alpha d minus 1, right? From a single electron traveling from the cathode surface to the anode surface. So during the traveling, the electron will cause ionization of gas, because the electron gain energy from electrical field and then collide with neutral atoms in the gas phase, so that they are newly generated electron and ion pairs. Okay? And when the ions in the discharge tube arrive the surface of cathode, the ion also gain energy from electrical field and collide with the surface of cathode. During the reaction, the bombardment reaction, the surface of cathode will emit electrons, and the factor is gamma factor. For the ion impacting the solid electrode, the surface of the solid will emit electron out. Okay, and this ratio is known as the gamma factor. And in the gas phase, the neutral gas will be ionized by high energy electron. And this reaction can be described by the alpha factor, or from this equation, the var epsilon factor. So yesterday we have already known the meaning, the physical meaning of this equation. So after multiple paths of the electrons and ions traveling between cathode and anode, the total number of electrons generated can be represented by a series equation. And this equation equals to m. M is the multiplication coefficient of discharge. So if gamma times in the bracket exponential alpha d minus 1 equals to 1, then the m will become infinite. And this condition will cause gas breakdown. Okay? So gamma times exponential alpha d minus 1 equal 1, or gamma times exponential var epsilon v minus 1 equal 1 is called a Thomson criterion to reach gas breakdown in a DC discharge tube. Var epsilon is the first Thomson coefficient, and gamma is the second Thomson coefficient. Okay. So later on, Chapman analyzed the discharge IV curve from a tungsten semi-empirical relation. Analyzed the curves alpha versus E is the electrical field, or the alpha over P is pressure, versus E over P. Okay, so in the left curves, the alpha and the E follows this Townsend's semi-empirical relation. Townsend's semi-empirical relation. So from this equation, there's a factor A and a factor B, right? And E over P is a variable. Okay, so one can control the electrical field and control pressure to change them, right? And get a different alpha. Alpha is related to the ionization capability in a discharge system. Okay, and then Chapman ran experiments. So the Chapman change pressure times the distance between cathode and anode, change these values. So the variable in this figure is P times D. So in a discharge tube, if you fix the distance between cathode and the anode, right? If the distance is fixed, you can change the gas pressure. So the PD value will change. And then you can run experiments, to get the breakdown voltage for your discharge tube. So actually the breakdown voltage is affected by gas pressure times the distance between cathode and anode. So Townsend and Chapman did these experiments and analyzed the curve and find out there's a general V-shaped curve for the discharge system. So the vertical axis is the breakdown voltage. So when you apply voltage across cathode and anode, right, we need to increase the voltage gradually. So at the beginning, the gas is insulating condition. And when the voltage reach breakdown voltage, so all of a sudden, the gas will be ionized, partially ionized, and converted to plasma state. And the gas become conducting state. So this voltage is named breakdown voltage. So that from these empirical curves, we can find out the breakdown voltage will change with the PD value. And here is the minimum breakdown voltage. So yesterday we have already seen these two figures. So the upper figure shows the breakdown for several cases. Right? So for this curve is for hydrogen, nitrogen, argon. So for these cases, you can run experiment and get the breakdown voltage versus the PD. And the upper curve is plotted in logarithmic scale. And the lower curve is plotted with a linear scale. Okay, so from this video, if we look at hydrogen, the patching curve follow this line, follow this line. So the minimum breakdown voltage is around a little bit higher than 200 or maybe 300 volts here. And the PD value for the minimum breakdown voltage is around 1 centimeter times tau. 1 centimeter times tau. Okay. And if you increase the PD value to 2 centimeter tau, the breakdown voltage will increase a little bit. Okay. So this part is the plot in a linear scale, and the upper figure is plotted with log scale. Log scale. Okay. And for air, the curve, right? This one is the air, discharge of air. So the minimum breakdown voltage for air is around 360 volts. So if you just run experiment by filling the gas tube, the quartz tube with air, and control the pressure, so that the pressure times the distance between cathode and anode, right, fall in this region, for air, fall in this region, from 0.4 to maybe also 2.0. You can use a power supply with voltage less than 400 volts. You can generate plasma with air as the working gas. With air as the working gas, okay. So, so there are reasons for the patching curve. So yesterday we know the left side of this curve is called the left-hand branch of patching curve, and the right side is the right-hand branch of patching curve. So at the left side of the patching curve, the PD value is very small. So usually, if we fix the distance between cathode and anode, the left-hand branch means the condition, the pressure for your discharge system is very small. So if your if the distance between cathode and anode is 1 centimeter, or such a small distance, if it is 1 centimeter, the pressure here is 10 to minus 1 torr. 10 to minus 1 or 2 times 10 to minus 1. So with such a low pressure, in a low pressure region, it's difficult to generate plasma. Okay. And in this region, because the density of the gas molecule, is small. So when the electron travel for a distance around 1 centimeter, they might not collide with another, and collide with gas atom. So the collisional frequency is very small. Okay, and in order to generate plasma, or for the sustaining of the plasma, we need to generate electron and ion pair by electron impact ionization. And since the gas density is very small, so the collision numbers are very small. So some of the electrons might collide with the chamber wall, right, without colliding with gas molecule. They will just travel for a short distance and then collide with chamber wall. Okay. So in order to get high enough ionization rate, but all the collisions must be effective. So in this way, in this case, energy of electron must be very high to ensure all the collisional process can generate electron and ion pair. Okay, and in a discharge tube, the only way to increase the electron energy is by increasing electrical field, right? And if the distance between cathode and anode is fixed, you need to apply higher voltage to generate higher electrical field. So that's the reason the breakdown voltage will become higher at this region, left branch of the patching curve, left hand of patching curve, because of the gas density is too small. And in the right hand branch, high PD value, the gas density is very high, so that the mean free path become very small. Mean free path becomes small. And from the previous slide, we know electron can gain energy from electrical field. So if the electron travel for longer time or longer distance, the energy of electron will be higher, right? When electrons travel in a region, in a space with fixed electrical field. But since the mean free path of gas is very small, there are plenty of gas atoms, so that even though the distance between cathode and anode is fixed, right, and there's an electrical field equals to the applied voltage divided by the distance between cathode and anode. Okay, but when electrons travel from cathode to the anode, they cannot travel all the way without collision. So electron might just only travel for a short distance, and then they will collide with gas atoms and change their direction, so that the electron cannot gain energy continuously. Okay, so if electron only travel for a short time or a short distance, let's see. Oh, this in the other slide. Okay. So if the electron only travel for a very short time and then they collide with gas atom, they can only get this amount of energy from electrical field. So in order to increase energy of electron, one need to increase electrical field. Okay, because the time for the electron travel freely is very limited, very small, in a system with high gas density. So the only way to increase the energy of electron is by increase the electrical field. So that's the right hand branch. Okay. Right hand branch of the patching curve. Okay. Okay. And later on we can see the values of the PD for different discharge gases and different electron material. Because again, the breakdown voltage is a function of gamma here, okay? And the parameter A and B is related to alpha. So again, the Paschen curve, the minimum breakdown voltage, this region, is related to the first Thomson coefficient and the second Thomson coefficient. They are related. Okay, so next few slides, I will go through a few types of gas discharge. So from the IV characteristic curve, or the IV or VI characteristic curve. The first important self-sustaining plasma is corona. Corona is a weak plasma, and then glow, and then arc. So there are three major important plasmas we can use to run materials processing. Okay, so this is the first discharge. Is a corona discharge. First, a self-sustaining discharge. Corona discharge. So in this figure, we can see here is a metal wire. Here is a metal wire. So if we have a wire, metal wire, or a point of electrode, sharp point of electrode, and when we apply the apply voltage to a piece of metal wire or to a sharp point of electrode, the electrical field will concentrate it near the surface of the wire. Near the surface of the wire, okay. And the left figure shows the top view. The top view look from this direction of the corona discharge system. So at the center of this figure is the cross section of metal wire with a diameter of A. A is the diameter of metal wire, right? And this circle shows a cylindrical electrode, right? And here is a wire electrode. And if we apply voltage between the center wire electrode and the cylindrical electrode, we can generate electrical field. In this region. But such kind of the setup, the electrical field near the surface of the wire, the electrical field is higher. The electrical field will concentrate near the surface of the sharp tip or metal wires. Okay. So if we apply a positive bias to the wire and then generate plasma, we can see a thin and continuous plasma covering the metal wire. So the plasma will just present here at this place, covering the positive biased wire. Okay, and this kind of plasma is weak. The density is very weak, and it belongs to the corona discharge or positive corona. And if we apply negative bias to the wire, and we can also get plasma. But this type of plasma, negative corona, there is a thin layer. Also, there is a very thin layer of plasma covering the wire, and there are some spots, bright spots, distributed over the wire. This is the negative corona. Okay, so it's a short reddish spray, right, merges into a continuous sheath. Okay. So typical. This is a typical form of corona, and it is the weakest form of self-sustaining discharge. Weakest form of self-sustaining discharge. Okay. And the corona can be generated at 1 atmospheric pressure, and in air. So if the corona is generated in air, there will be a chemical reaction because the air is composed of 79% of nitrogen gas and 21%, about 21% of oxygen. And in air, there are also water vapor or moisture, and carbon dioxide. So these equations shows the chemical reactions for the positive corona and the negative corona. And there are some important part here. So for example, in the positive corona, you might get hydronium ions. So this ion is a kind of acid. And in the negative corona, one can get oxygen radical. And when oxygen radical react with oxygen molecule, they will form ozone. Right, ozone molecule. Ozone is highly reactive. Okay, so people use the corona to generate ozone for in industry. Okay, and maybe in our home appliance, we also use ozone generator to clean air, or we can also let the ozone dissolve in water to clean vegetables or fruits. Okay, ozone. Okay, and in this place, if the ozone or oxygen anion reacts with carbon dioxide, they might form CO3. This again is an acid. So actually, these products are acids and corrosive to some material. So we can see in the outdoor, we can see electrical cables. So the Thai Power company send out the electricity to our home or to a factory with very high voltage. So for long distance electricity transportation, they might use a voltage higher than few thousand volts, and then reduce the voltage to 400 volts, and then 220 volts to our home. Okay, so with such high voltage of the applied to the metal wire, and then the metal wire is covered with a PVC, a polymer polymer material as their insulating sheath. Insulating sheath, right? PVC, a polymer material. So if they are the ozons or other highly reactive medium generated in the corona, the ozone or this species start corrode the plastic. The surface of plastic. So if the plastic, if the PVC coating on the copper wire is degraded. So eventually the metal wire, copper wire will expose to air. And they might get corrosive, or they might get a shortage. So that there will be some dangerous thing happen. Okay. Okay. But in industry, people generate ozone, generate corona, and use the ozone to treat surface of plastic. So usually the plastic is hydrophobic. You know that, hydrophobic. Hydrophobic. So it means on the surface of plastic, if you drop a droplet of water on the surface of a piece of plastic. So this is plastic. If you let a droplet of water stay on the surface of plastic, they might look like this way. Hydrophobic surface, okay? And if you use plasma to treat the surface of plastic, the surface will change to hydrophilic. Okay? So that the surface of plastic is here, and if you treat the surface with ozone or with corona discharge in air, the surface condition change to hydrophilic. So if you let one droplet of water stay on the surface of the plastic, they might look like this way. They might change the surface property from hydrophobic to hydrophilic. Okay, so after you make the ozone treatment on the surface of the plastic, and then you can let other materials to adhere on the surface of plastic. Okay, otherwise it's difficult to let other materials to adhere on the surface of plastic. So industry use this way to change or to modify the surface of plastic from hydrophobic to hydrophilic. Okay. So the surface can then, for the next step, they can be coated with different materials, and by using a vacuum metallization, electroplating, and also you can coat organic materials on the surface of plastic. Okay. a corona discharge. Also forms a curve just like a patching curve, right? Like a patching curve, which we have already seen in previous slide. So this is the breakdown characteristics of coronas. So in this figure, the horizontal axis is P times A. So A is the diameter of metal wire. In this figure, the horizontal axis is the pressure times diameter of metal wire. Okay. And the unit here, millimeter mercury height. Millimeter mercury height, right? This unit equals to torr. This is the unit. So it's torr times centimeter here, right? This is the unit for pressure, millimeter mercury height. For 1 atmospheric pressure is 760 millimeter mercury height, right? Is equal to 760 torr. After the Italian scientist, torr. And the vertical axis here is A times E. E is the electrical field. So A again is the diameter of the metal wire. So the electrical field times the length equal to a voltage. So again, the vertical axis is the breakdown voltage for the corona discharge. Okay, so this part is the left hand branch of patching curve, and this part is the right hand branch of patching curve. And from this figure, you can find out here is a minimum of breakdown voltage. So again, you can find out the way, the easiest way to generate corona discharge. Okay, if the P times A value is not very small, so for example, if it is less than 0.1 torr centimeter, so if you have a small diameter of wire, okay, the electrical field will concentrate it on the surface of the metal wire. So at least near the surface of the metal wire, the gases are easily to be ionized. Okay, and this curve can be described by the equation here. E is the electrical field equals to the applied voltage divided by R times natural log B over A. So A is the diameter of the metal wire here, right? B is the radius of the cylindrical electrode. R, so R is R. So at any point here, right? You can measure the distance between this position and the center of the metal wire. So this is R. So from this equation, we can know that the electrical field, the distribution of electrical field is not uniform across the radial direction. It's not uniform. It's not uniform, okay? because R is here. But it's a function of the natural log B over A for your system. Okay, for your system, okay. And at the surface of the metal wire, R equals to A, so that the breakdown electrical field equals to the breakdown voltage divided by A times natural log B over A. So this is an analysis of the curve or the breakdown of corona discharge. So one can know the breakdown field for the corona discharge depends on the geometry factors or geometry dimensions of the metal wires and the cylindrical electrode surrounding the metal wire. Okay. If we let the current of the discharge increase, the glow discharge, the plasma falls in the glow discharge region. And the glow discharge regions includes subnormal glow, normal glow, and abnormal glow. 3 regions. So in the subnormal glow region, when the current density increase, the voltage decrease from the IV characteristic curve, right? In normal glow, when we increase the current density, the voltage remain constant. And for the abnormal glow, when we increase both current density, the voltage will also increase. So this part is called abnormal glow. So in industry, the people use normal glow to run plasma enhanced chemical vapor deposition process or plasma etching. Okay. And for the abnormal glow, since the voltage of the discharge can be increased, so that the ion energy can also be increased. Ion energy. Okay. So people use high energy ion to collide with surface of cathode and then knock out atoms from cathode surface. And this process is named sputtering. And if you collected the atoms knock out from the cathode, and you collect the atoms on a piece of substrate, you can get a thin coating. And this process is named sputter deposition. So abnormal glow can be used for the sputtering and sputter deposition process. Normal glow can be used for plasma enhanced chemical vapor deposition and dry etching. So in our class, I will introduce the PECVD in one chapter and sputtering in another chapter. We can see a little bit more about the parameters and the design rule for the plasma in these two kinds of system. Right. And since the current density in the glow region, right? Current density is higher than the corona, the current density. And we have already known when we generate plasma, the plasma will become luminous. It means the plasma will emit light, right? So it's luminous. So if the current density is higher, the light intensity coming out from plasma will also become higher. Okay. So in this region, we can see the plasma glow by bare eyes. But in corona discharge, usually the plasma is very weak. So it's hard to see the glow. But in this region, we can see the plasma by bare eyes. So these parts are named glow discharge. Okay.